Okay, so I'd like to welcome everybody to the second section of types at this year's POPL. As a reminder, we have, if you want to ask questions after the talk, there's Meet. If you're online or indeed, you can do that in person as well. And if you're going to ask a question in the room, please state your name and affiliation before launching into your insightful question. So we're going to kick off this morning with a couple of related talks on merging types and solutions to the expression problem. And so we're going to start with a talk about emph, presented by Nick here.
Thank you, Alan. And thank you all for making out this morning. I'm talking about today joint work with my advisor at the University of Pennsylvania and our collaborators at the University of Hong Kong. This work is all about bringing more compositional language features to programmers. And in particular, we're going to talk about a language feature called the merge operator. The merge operator does one job. It takes two values, and it combines them together. It takes all the information from each value, and it produces a new value that has sort of all of the information, all the functionality of the two that you gave to it. So an example here is record concatenation. You can take smaller records and combine them into bigger records. And with this feature, there's been a lot of work on compositional language design. So we've seen things like row polymorphism encoded using the merge operator, first class traits, and as we'll see today, you can encode expression problem solutions using it. But for all the power the merge operator gives us, it also is a bit of an unwieldy beast. It can introduce potentially non-deterministic expressions or values into the language. So for example, while concatenating records is pretty straightforward and deterministic and makes a lot of sense, what happens if you merge true with false? Well, how do we even define the semantics of an if statement on this value? Well, there are a couple things that you might try to do. You might just say, well, the left side of the merge takes precedence, and so we'll always just take the left side. But that makes your merge not commutative. And I mean, that makes programs much harder to reason about as they grow large. Another thing you might do is non-deterministically pick one of the arguments of the merge operator in this situation. But we want to keep our languages deterministic because non-determinism can also be hard to reason about for the programmer. So there's existing work here that uses the type system to give us the power of the merge operator, but keep our language deterministic. The idea here is that we have a relation in the type system called Mergeability, and it tells us that which types can be merged with which other types. In this case, true and false would not be allowed to be merged because Huang is not mergeable with Huang. So this is all well and good, but non-determinism gets even harder to prevent in the presence of union types and overloading. And so these are the language features we're going to look at today. Our work introduces a core language called emph. It's deterministic, it's type safe, and it has the merge operator, and it has overloading, and it has union types. The two keys to making this all work are two relations that are dual to each other. We call them disjointness relations. We call them, one is mergeability, and the other is distinguishability. That's sort of the key in the type system, and the key in the operational semantics is performing ADA extension at runtime. So once we look at these features of the language, we're going to go look at an example, and we'll see later. We would like to be able to encode a simple arithmetic language that has addition and integer literal expressions, and we want to write an evaluator for that language, and we want to take that evaluator and extend it with support for floating point literals. And once you add new kinds of literals, that automatically sort of means your addition operator now has to be overloaded to support everything in the language. But first, let's take a look at the type system. These are the types in emph. We have type variables, we have type constructors, we have functions, polymorphic types, bottom, top, and union and intersection. We do have some restrictions on which unions and intersections are considered well formed that you can see in the paper. On top of the types, we have a fairly conventional subtyping relation, and we have sort of one interesting feature of it here that's sort of important for this compositionality work is that the intersection union types can distribute over various type constructors in the language. So this is the example of the intersection type distributing over the function types. So we give a bidirectional type system for this language, and the key rule is this rule for the merge operator. It says that when you merge some value of type A1 with some value of type A2, first we have to check and make sure that A1 is mergeable with A2. And we check that according to the mergeability relation, which is denoted with the Bowtie operator. So at that point, if the merge is allowed, then we have a value that functions as both an A1 and an A2. So we assign an intersection type A1 intersect A2. But which types should be mergeable? Well, the purpose here is to only allow types to be mergeable so long as we know that we can use them in an unambiguous way. That means that for any operation that is performed upon this merged value, we need to know which of the components of the merge are going to be operated on. So the merge is unambiguous when there's sort of no shared operation between all of the components of the merge that might cause nondeterminism. So for example, it's always safe to merge two records with disjoint fields. That's because when you project a field out, you always know which component of the record the projection applies to. On the other hand, it gets a little bit trickier when you have overlapping fields. In those cases, we make sure that the contents of the overlapping fields are mergeable with each other, so we can merge the contents recursively. The top type is really easy to deal with. It can be merged with anything because there's no operation on top that might be ambiguous. And again, intersections denote merges here. So A intersect A prime represents a values of type A merged with values of type A prime. If we want to perform another merge and merge that merge with a value of type B, then we had better make sure that B is mergeable with both of the values that have already been merged. The rules get a little bit more interesting for function types. We can merge two functions that accept the same input by recursively merging the output of the function. And so in the type system, this says that when you have two functions with the same domain, then you need to recursively make sure that the outputs of the functions are mergeable. On the other hand, sometimes you want to merge functions that handle different inputs. That's overloading. So when you do that, you need to make sure that given any input, we can figure out which of the overloads should be dispatched. So in other words, we need some way to distinguish, if A and B are the inputs to two overloads, we need to make sure that there's some way to distinguish all of the values of type A from all of the values of type B. This is a little non-trivial in our system because we don't carry around any runtime type information. So this distinguishability relation here has to sort of account for the fact that some values have information with them at runtime telling you some information about how, which overload they're in or which type they have, but other types of values might not. So to explain that a little bit better, we're going to call two types distinguishable when we can tell their values apart using pattern matching. So for example, two different data constructors are always going to be distinguishable from each other because we can always pattern match them into two different branches. But on the other hand, function types, regardless of what the domain and range are never distinguishable from each other. And that's because if you take two lambdas, there's no way to tell which of the two function types they are. There's no type information that you can get from those lambdas. There's no information you can get at all except for trying to run them. So it turns out that these two relations that we just described are dual to one another. Like I just said, we call two types distinguishable when we can distinguish their values using pattern matching. Interestingly, there's a dual view on mergeability, which says that two types should be mergeable when we can tell their contexts apart, given that one of the contexts has a whole of type A and the other has a whole of type B. And in the paper, we really push this duality to the limit, and we show that this sort of corresponds to co-pattern matching. So to understand the sort of design space here, let's look at this program. All it does is it matches on E, and if E is a Boolean, it runs one branch, and if it's an integer, it runs the other branch. That seems innocuous enough. But when you have merge, it can be a problem. That's because you might have a merge of a Boolean with an integer, and then which branch should run? Well, we want to avoid ambiguity here, of running both branches and merging true with false. So we need to choose. We can either allow the merge of one with true, or we can allow this pattern match of booleans into one branch and integers in the other. But we cannot allow both. Or another way of saying this is that boolean and integer can be distinguishable, or they could be mergeable, but they can't be both distinguishable and mergeable. And so, and that's sort of a general principle in FBO. No two types that are inhabited should be both distinguishable and mergeable from each other. So that means that we have design decisions to make. Which pairs of types should be mergeable and which should be distinguishable? Well, for this, we look to ideas from polarized type theory. It turns out we can use the polarity of the type to determine whether they are naturally mergeable or distinguishable from each other. So positive types are those that are easily pattern matched on, things like booleans, integers, and sums. And since distinguishability has to do with determining whether the values in one type can be pattern matched, can be distinguished from the values of another type using pattern matching, it's very natural to say if two types are positive, then we'll choose to make them distinguishable from each other. And on the other hand, negative types are those types like function types that you don't pattern match on. And so it makes sense to make those types mergeable with each other. All right, so you've now seen the key idea in the type system. Let's take a look at the operational semantics. So this is the key example here that sort of drives the design of our operational semantics. We have a record that has two fields, L and K, and we assign that record to the variable X. But the type annotation on X only mentions K. It doesn't mention L. And because of that, the programmer can later on add the L field back using the merge operator. And so the question is this program ambiguous? What should the value, if we project out L at the end, what should the value that we get back be? Should it be the original value or the value we added later? And the idea here is if you want to be able to think in terms of the abstractions that your type system offers, this program should be unambiguous. Because the programmer, once you annotate X with the record type that does not mention L, the programmer should no longer have to think about that type. That's a fairly natural idea for the programmer, but it has an interesting consequence that means that the type annotations are actually doing something at runtime here. The type annotations have computational meaning. They're not just inert. What are type annotations doing exactly? Right, here we just saw that the type annotation in X is kind of hiding in the field L. What does that mean? How do we describe that more generally? Well, there's been some work that does this kind of thing, and it says that basically it defines a special reduction relation that takes a value and it takes a type annotation, and it erases all the extra information that's in the value but not in the type annotation. We do something slightly different. We actually instead build a wrapper around the value, and we build that wrapper according to the type annotation, and we make sure that the wrapper only exposes the information that the type annotation mentions. This is kind of similar to how higher contracts work. And in fact, this isn't really a novel idea at all, because it's exactly the expansion for the record type. And so we started with a value v that might have been a record with many fields. We annotated it with a record type that only mentioned one field. And the idea here is that we built up a new record that only exposes that one field to k. So the lesson here is that at runtime, we want to ADA expand the type annotations in the program to make sure that everything stays deterministic and no values expose more information than what their types say they should expose. So that's a key idea in the operational semantics. Let's see how it sort of all fits together and return to the example that I mentioned earlier. Again, we want to define an evaluator for a simple arithmetic language that supports integer literals and an addition operator. And we want to take that language and we want to extend it with floating point literals. That means that the addition operator will now be overloaded. And in the process, we want to make sure that we don't have to redo any work. We don't want to duplicate any of the definitions that we originally started with, or that we originally wrote for the simple language with just integers. To do this, we're going to encode our data types in a style known, well, essentially using church encodings, or a style sometimes called finally tagless style. And that involves defining an interpretation, what it means to be an interpretation of an integer expression, as an arbitrary type A. So this type tells you, the constant field in this record tells you how to interpret an integer constant as some type A. And the addition field tells you, well, if you have two interpretations of two expressions, how do I add them together to get a new interpretation? So they correspond to the constructors in the language, how you build up terms. To actually build a term now, you need to specify it by its fold. So this expression 3 here takes an interpretation at some type alpha and returns you an alpha, basically implements fold. And then we can define an interpretation of an expression, such as evaluate how to evaluate an expression as an integer. In this case, it's really simple. We just give the identity function for constants, which just pulls out the meta-level integer, and then addition is just implemented using meta-level integer addition. And then we can do exactly the same thing for floating points, if we so choose, and the only difference here is that we're using floating point addition. We can take now we want to define the type of the combined language with integers and floats. And there are a couple ways to do this, but one way to do this is to start with the type that we used for integer expressions, and just add one little piece of information, which is the floating point constants here. And we can do that with an intersection type. So if we take this intersection type here and we expand the definition of the integer arithmetic expressions, and we distribute the intersection over the record, then we end up with this type. And we can distribute the intersection further, and we end up with this type, which is actually the type you probably would have written if you just tried to define infloat arith expr from the beginning without composing the things together that we already have. Right, okay, so now recall that we have evaluators for integers, and we have evaluators for floats. And we want an evaluator for the combined language. Well, we can start to build that evaluator simply by merging the integer evaluator with the floating point evaluator. But we're not quite done yet. And that's because we now in this sort of combined language, there's a possibility that you might add an integer with a float. And neither of our evaluators that we started with accounted for that possibility. So here's an example of an expression that does that here. So we still have work to do. And the work that we have left to do is represented by this arithmetic extension type. And it shows that we still have two cases of the addition function that we need to specify in our evaluator. How to add ints with floats and how to add floats with ints. We can write that extension and we just implement it by coercing integers to floats and then using floating point addition. Now all we need to do is take that extension and merge it with the evaluator that we've been working on so far. And we're done. We now have the evaluator for the combined language. So that was pretty quick. What did we do? We took the type of integer expressions, we extended it to the type of integer and float expressions. We took the integer evaluator and we extended it to be an integer and floating point expression evaluator. And we did so only by adding functionality, not by having to repeat any of the functionality we started with. In terms of the expression problem, this is essentially adding a new case to a data type. And we can also add new operations to data types very easily. All we have to do is define another interpretation, just like we did for the evaluator. So, in conclusion, FCO shows how to combine the merge operator with overloading and union types, and while keeping everything type safe and deterministic. The key ideas in the type system are mergeability and distinguishability, and the key idea in the operational semantics is to expand type annotations up runtime. We proved type soundness via progressive reservation, and we also proved the determinism of FCO all on paper. But we did formalize important meta theory about subtyping and disjointness in common. That's it. Thanks for coming to the talk.
Okay, so we've got 5 minutes for questions.
John Boylan at the University of Wisconsin-Milwaukee. Very nice talk. It's a very clean system. I like this. I'm going to ask a question. I missed. Let's say you only did the partial part. You did that, or you didn't add the adding inst floats part. Would there be type error if you tried to apply this, or how would the system know that you had the missing part?
Well, you have a valid expression, but it has a type that doesn't allow you to do very much with it. you can't evaluate expressions that have both floating point and integers in them. You get type error in track.
Thanks, Andrew Hirsch at the University of Buffalo. Another question about that example. Is it possible to tell what is missing from that function that you create automatically, or is that just something the programmer needs to be able to intuit?
In theory, I think there is a way to do it automatically. In fact, maybe the ideas in the next talk might be helpful here. Is you kind of need to figure out the difference between the type you want in the end and the type that you've built so far. So I think that you probably could automatically calculate that, but we don't talk about that.
So James Noble from Nowhere currently. Very nice talk, nice work. So you've got mergeability and distinguishability, and you said a type was either. Is there, do you know that relationship between all types, or are there types where you're not sure whether they're mergeable or distinguishable?
It's kind of a design decision on the programmer's part, or sorry, on the language designer's part. In most cases, you could make either decision for any pair of types, or you could leave some types to be neither mergeable nor distinguishable.
Okay, right. And that just kind of leads to the follow-up, which is, given what's interesting in superposition and quantum computing, shouldn't we be able to merge Boolean with Boolean and then have the cat both alive and dead?
Sure, then you have you have non-determinism in your system, right? But the point of our work is how to have merged but keep everything deterministic.
Okay, so I've got a question, which is about like everything becomes horrible once you put mutation into a language, and do you have a feeling for what the system would look like if you had mutation?
I haven't looked at it too much. I can't think of any problems that would arise off the top of my head.
Well, I mean, the thing I was wondering about is that coercion operation you thought when you upcast, that's now a destructive operation. It's removing fields from a record, and that's fine because everything here is immutable. But in the case of mutation, are you actually updating the object? And if so, there may be aliases to it who are expecting that field to be there.
Yeah, I'm not quite sure how that would work.
I think with my session here, that's when all of us to shut up.
Rotated online.
Yes, take it offline. All right, question back.
Is there any support for parametric types? And if so, does mergeability or distinguishability constraint show up?
Yeah, so we have polymorphism in the language, like system-style polymorphism. And Passport also has disjoint polymorphism, where you can quantify over a type variable and provide certain disjointness constraints on that type variable. We don't have that in POPL right now, but it's a very natural feature to have.
I think we should thank the speaker.